Introduction. To the human eye, the light appears to be passing through the atmosphere, as atmosphere is transparent to the incoming solar radiation. However, atmospheric gases are having selective scattering light of different wavelength. The gases also absorb electromagnetic energy at specific wavelength intervals called absorption bands. The intervening regions of high energy transmissions are called atmospheric transmission bands or windows. The sun is primary source of radiation, and electromagnetic radiation from the sun is reflected by the earth and detected by the satellite or aircraft. Bonds must pass through the atmosphere twice. Once it has to pass from the sun to the earth's surface, and after being reflected by the surface of the earth back to the sensors. These interaction of solar radiance and reflected radiation from the target on the earth's surface with the atmosphere constitutes interference with the process of remote sensing called as atmospheric effect. In this chapter, we will discuss about different interactions, that is refraction, scattering, absorption, reflection, transmission. Particles and gases present in the atmosphere interact with the incoming light and reflect or emit radiation. Our interest in this interaction is related to the fact that atmospheric components like diffuse, reflect, absorb and emit electromagnetic radiation, changing the original radiation of the object observed by remote sensing sensors. The interaction of the electromagnetic radiation with the atmosphere is important to remote sensing for two main reasons. Information carried by electromagnetic radiation reflected or emitted by the earth's surface is modified while transversing through the atmosphere. Interaction of electromagnetic radiation with the atmosphere can be used to obtain useful information about the atmosphere itself. The change in the incident radiation on its way towards the satellite is governed by several atmospheric effects. Effects are caused by mechanisms of diffraction, scattering, absorption and transmission. Refraction. Atmospheric refraction is a deviation of the electromagnetic waves from a straight line as it passes through the atmosphere due to the variations in the air density which varies with altitude. Near ground, the atmospheric refraction produces mirages, and this can change the look of the distant objects. Atmospheric refraction causes astronomical objects to appear higher in sky than they are in the reality. The refraction affects the complete spectrum of the electromagnetic radiation in varying degree. For example, in visible light, where blue is more affected than red, the amount of atmospheric refraction is a function of temperature, pressure and humidity. Even the turbulence in air makes atmospheric refraction inhomogeneous. This is the cause of twinkling of stars and deformation of the shape of the earth at sunset, sunrise. Atmospheric refraction is minimum in the zenith and maximum at the horizon. In day-to-day life, often experience refraction when we insert a spoon in a water filled and the horizon, the optical part of the light through the atmosphere is very long, and the atmosphere usually has the layer structure of different temperature, gradient and pressure. Refraction of light by these layers can cause sun disk to be deformed, flattened or distorted. Scattering. The light which we see by our eyes is not directly from the source, but indirectly by the process of scattering of light field. When you look up the sky, sometimes you may see the diffused to scattered solar radiation when you look at clouds, or a sky starting is a very important consideration in remote sensing investigation, because it can surely reduce the information content of the remote sensed today to the point that the imagery loses contrast, and then it becomes difficult to differentiate one from the other. Scattering is a process in which electromagnetic radiation interacts with the particles or large gas molecules present in the atmosphere and causes it to be redirected in all directions from its original path by reflection or refraction. Scattering depends upon several factors such as wavelength of the radiation, the abundance of the particles or gases and the distance the radiation travels through atmosphere. We read in atmosphere that the colorful examples of scattering generated by molecules are resulted in clouds and magnificent rainbows and halo effects are few examples of optical phenomena due to scattering. Scattering is a process associated with light and its interaction with matter. It covers at all wavelength covering the entire electromagnetic spectrum. The amount of scattering depends upon the size in the abundance of the particles, the wavelength of radiation in the depth of the atmosphere through which the energy is travelling with where both are present. The scattering will be uneven especially and will vary from time to time. Scattering reduces image contrast and changes spectral signature of the ground objects as seen by the sensors. There are two types of scattering phenomena can be observed: isotropic scattering and anisotropic scattering. Anisotropic scattering. Isotropic scattering is different from reflection in the same that the direction associated with scattering is unpredictable, whereas the direction of the reflection is predictable. Anisotropic scattering is a property of being directionally dependent as opposed to isotropic, come up with the implies identical properties in all directions. In that much feared, the particles responsible for scattering cover the size from gas molecules, that is 10 to the power of 8 centimeters, to large raindrops or hailed particles. Relative intensity of the scattering particles depends strongly on the ratio of the particle size to the wavelength of the incident. If in the scattering isotropy, the scattering pattern tends to scatter light equally into the forward and rear direction. When the particles become larger, the scattering energy is increasingly concentrated in the forward direction with greater complexity. Radiation scattered from a particle is a function of several things such as shape, size, index of refraction of the particle, wavelength of radiance, and the surface geometry. Depending on the size of the matter, there are two types of scattering takes place: selective scattering and non-selective scattering. Selective scattering. When scattering is observed with a dependent wavelength, it is known as selective scattering. Selective scattering is of two types: relay scattering and Mie scattering. Relay scattering. Relay scattering is caused by a very small particles and glass molecules with radii for less than the wavelength of electromagnetic radiation of interest. Primarily, it occurs due to the oxygen and nitrogen molecules in the sky. Thus, it is known as the molecular scattering. Relay scattering can be considered to be elastic scattering since the photon energy of the scattered photon is not charged. Scattering in which the scattered photons have either higher or lower photon energy is called Raman scattering. Usually, this kind of scattering involves exciting of some vibrational modes of the molecules, giving the lower scattered photon energy, scattering of an exciting vibrational state of a molecule which adds its vibrational energy to the incident photon. Since the extent of the scattering is inversely proportional to the fourth power of the wavelength, comments shorter wavelength such as blue light is visible spectrum affected the most. The relay scattering is also responsible for the red sunset. During sunset, calmer sunlight passes through a longer path of air at noon. Since the violet and blue wavelength are scattered more during their long path through the air, hence what we see at a sunset is a residue, that is the wavelength of the sunlight that are hardly scattered away, especially the oranges and the reds. The sky appears to be blue because of the sun's light passing through the atmospheric, which is more shorter wavelength of visible spectrum, are scattered more than the other visible wavelength. However, during the sunrise and sunset, sky appears to be red because during the sunrise and sunset, the light has to travel through the atmosphere than the midday, and the scattering of the shorter wavelength is more complex. This leaves a greater proportion of the longer wavelength light, that is red, to penetrate the atmosphere. Mie scattering. Mie scattering occurs when the particles in the atmosphere are of the same size as the wavelength being stated. It is caused by the particles that is between 0.1 and 10 UM, such as dust, smoke and salt for examples. Dust, smoke and water vapor forms is causes of the Mie scattering, which tends to affect longer wavelengths. Mie scattering occurs mostly in the lower of the atmosphere, where large particles are more abundant and dominates when cloud conditions are overcast. The amount of scattering is greater than the relay scattering. The violet and blue light scattered away more with the increasing amount of smoke and dust particles in the atmosphere, and only the longer orange and red wavelength light reaches our eyes. Non-selective scattering. Non-selective scattering are wavelength independent. It is caused by particles such as water droplets, ice fragments of cloud whose radii exceeds 10 UM. The scattering is independent of the wavelength. All the wavelengths are scattered equally and not just blue, green and red. Non-selective scattering takes place in the lower portions of the atmosphere, where there are particles more than 10 times the wavelength of the incident electromagnetic radiation. The most common example of non-selective scattering is the appearance of clouds as white. As clouds consist of water droplets, particles, and the wavelength are scattered in equal amount, the clouds appear as white. Water droplets and large dust particles can cause this type of scattering and thus cause fogs and clouds to appear white to our eyes, because blue, green and red light are all scattered in approximately equal quantities. Scattering creates the effects of haziness in remote sensing images, which reduces the contrast in images. It also creates the adjacent effect, in which signal recorded in a pixel partly incorporates the scattered signal from the neighboring pixel. It is required to introduce an important term, that is the path radiance. The path radiation that has been scattered in the Earth atmosphere and has reached the sensor without contracting the Earth's surface is known as the path radiance. It is essential to remove the path radiance from the remote sensing images before any image analysis, particularly for multi-data images. Absorption. By the time electromagnetic radiation is recorded by a sensor, it has already passed through the Earth's atmosphere twice. Once while travelling from Sun to the Earth, and the second while travelling from the Earth to the sensor. When light travels through atmosphere, a gradual reduction in its intensity occurs. The reduction in intensity with distance in a medium, that is atmosphere, is called the attenuation of light. This attenuation occurs mainly because of scattering and absorption of light in atmosphere. Absorption is a process by which radiation, that is the radiant energy, is absorbed and converted into another form of energy such as heat or chemical energy. Absorption is a wavelength dependent. Absorption of light occurs because part of the incident light is transformed into the energy of motions of atoms in the medium. It can take place in the atmosphere or in the terrain. To understand it better, we can take examples of grass. Grass appears green because it scatters green light more effectively than red or blue light. Apparently, red and blue light incident on the grass is absorbed. The absorbed energy is converted into some other form and it is no longer present as red and blue light. In visible spectrum, absorption of energy is nearly absent in the molecular atmospheres. Clouds can also absorb very little visible light. Both scattering and absorption removes energy from the beam of light. Thus, the beam of light is attenuated and we call this attenuation extinction. There are three main atmospheric constituents which absorb solar radiation. The three constituents are ozone, carbon dioxide and water vapor. Ozone gas, which plays an important role in the Earth's energy balance, has maximum concentration in the stratosphere at altitude about 20 to 30 kilometers. Ozone absorbs high energy. It prevents short wavelength portion of the ultraviolet spectrum to transmit through the lower layers of atmosphere. Carbon dioxide, which occurs mainly in the lower atmosphere, absorbs the radiation in the mid and far infrared regions of the electromagnetic spectrum. Maximum absorptions occur in the regions from about 13 to 17.5 μm. Abundance of water vapor significantly varies with time and location. However, it is commonly present in the lower atmosphere. Water vapor contributes significantly to the absorption of radiation, particularly in several bands in between the regions of 5.5 and 7 μm. It is important to note all the media shows some sort of absorption. Media which absorbs all wavelength more or less equally are said to show general absorption, whereas media which absorb some wavelength more strongly than the others are said to show selective absorption. The ability of a medium to absorb energy is measured as absorptance. From remote sensing point of view, absorption in the visible, near infrared and thermal infrared regions of electromagnetic is important. Significant amount of absorption in visible and near infrared bands is basically due to molecular oxygen and ozone, water vapor, carbon dioxide and some other minor gases. Water vapor, carbon dioxide, ozone, methane and chlorofluorocarbons absorb radiation in thermal infrared band. As you know, windows are used as a motion for air ventilation and light. Similarly, there are certain portions of the electromagnetic spectrum where light can travel through the atmosphere with much absorption. The absorption by various constituents in the atmosphere results in limiting portions of the electromagnetic radiation from reaching the earth. Hence, the earth's atmosphere is not completely transparent to electromagnetic radiation. For remote sensing, this limits us to the portion of electromagnetic spectrum where radiation is strongly absorbed. This portion of the atmosphere is called atmospheric windows. Position, extent and effectiveness of atmospheric windows are determined by the absorption spectra of the atmospheric gases. Energy outside the atmospheric window is severely attenuated by the atmosphere, hence cannot be effective for remote sensing. The most important atmospheric windows are visible windows, the 3.7 μm window, the microwave window and the 8.5 to 12.5 μm window. The visible window is mainly affected by ozone absorption and by molecular scattering. The 8.5 to 12.5 μm infrared window is punctured by the 9.6 μm ozone absorption band and is affected by water absorption. The dark, that is black area, denotes regions of the electromagnetic spectrum where atmosphere absorbs most amount of the radiation, and the light grey regions are the atmospheric windows. The infrared channels are most often between 1 to 30 μm. The most common infrared band for meteorological satellite is in the 10 to 12.5 μm window, in which the atmosphere is relatively transparent to radiation upwelling from the earth's surface. Even in the atmospheric window region, scattering by the atmospheric constituents produce the spatial redistribution of energy. Reflection. When light travelling in a medium, that is atmosphere, encounters a surface leading to a second medium, that is another earth surface, part of the incident light is returned to the first medium from which it came. This phenomena is called reflection. In other words, reflection is a phenomena in which the incident radiation is returned back to the same medium due to the discontinuity of electromagnetic characteristics at the interface of the two media. Reflection occurs when a ray of light is redirected as it strikes a surface. Understanding of the reflection is important, since about a third of the energy from the sun is reflected. Transmission. When electromagnetic radiation is incident on the earth's surface, part of the energy gets scattered from the surface, which is known as surface scattering, and a part of energy gets transmitted into the medium. In homogeneous materials, the radiation is simply transmitted, but in inhomogeneous materials, the transmission radiation gets further scattered, which is known as volume scattering. The signal received by sensors is a combination of both processes, that is, the surface and volume scattering. The transmission of radiation occurs when the radiation passes through a substance without significant attenuations. the ability of a medium to transmit energy is measured as the transmittance, and it is defined as the ratio between the transmitted radiation and the incident radiation. Summary: the atmosphere constituents scatter and absorb the radiation, modify the radiation reflected from the target by attenuating it. Both scattering and absorption vary in their effect from one part of the spectrum to other. The solar energy is subjected to modification by several physical processes as it passes the atmosphere, that is scattering, absorption and refraction. Atmospheric scattering. Scattering is a redirection of electromagnetic radiation by particles suspended in the atmosphere or by large molecules of atmospheric gases or water vapor. The amount of scattering depends upon the size and the abundance of particles, the wavelength of radiation and the depth of the atmosphere through which the energy is travelling, which varies both in time and over season. Thus, scattering will be uneven spatially and will vary from time to time. Scattering reduces image contrast and changes spectral signatures of the ground objects as seen by the sensors. Atmospheric absorption. The gas molecules present in the atmosphere strongly absorb the electromagnetic radiation passing through the atmosphere in certain spectral bands. Mainly, three gases are responsible for the most of the absorption of solar radiation, that is ozone, carbon dioxide, water vapor. Absorption relatively reduces the amount of light that reaches our eye, making the scene look relatively duller. Atmospheric windows. The atmosphere selectively transmits energy of certain wavelength, the spectral band of which the atmosphere is relatively transparent are known as atmospheric windows. In the visible part, transmission is mainly affected by ozone absorption and by molecular scattering. Reflection. Of all the interactions in the reflective regions, surface reflectance are the most useful and revealing in remote sensing applications. Reflection occurs when a ray of light is redirected as it strikes a non-transparent surface. The reflection intensity depends upon the surface refractive index, absorption coefficient and the angles of incidence and reflection. Transmission. Transmission of the radiation occurs when the radiation passes through a substance without a significant annotation. For a given thickness or a depth of a substance, the ability of the medium to transit energy is measured as transmittance. T is equal to transmitted radiation by incident radiation.